Is the solution to question 8 from the 2015 examination paper for Master Graphics on Virtual Environments. Okay, so the first question says, explain what direct and global lighting models are and give advantages and disadvantages. So a direct lighting model is one that only considers light coming directly from a light source. Okay, this is different from the global lighting model, where considered light both reflecting from a light source and reflecting off of other objects in the scene. Okay. An advantage of direct lighting model is it's very quick to calculate because you're only considering light reflecting off a single object. A disadvantage are that it can give unrealistic results. Okay, so the application would be you'd use it in applications where you need it to be calculated quickly, i.e. in games, okay, where computational efficiency is important. The global lighting model, the advantages are that it gives realistic results, and the obvious disadvantage is that it's very computationally expensive. So you can't use it in computer games, but you can use it in things like films, where you can pre-render scenes where computational time isn't an issue. Okay, part B, the angle between a light source vector L and the normal to a plane is the same as the angle between the reflective vector R and the normal. So here we have our plane, and there's our normal vector. So if this is the vector pointing to the light source, then the vector reflected, or the light reflected, will follow R, which is the same angle between the normal vector. Okay, and you're also given the formula for the vector projection. So assuming that B is a unit vector, the projection of vector A onto B is the dot product between A and the unit vector B multiplied by the unit vector B. Okay, so the question says copy out the diagram and annotate it to show how R, the reflection vector, can be given in terms of L and N. Okay, so this is sort of built upon the diagram up here. The only difference is, instead of N hat, okay, I've got the projection of L onto N. So if L's there, if I draw a line across, my projection of L onto N is a vector that starts here and ends about here. So that's what I've got there. Okay, I've also picked up R and moved it to the end of L. So we've got L plus R ends up here, and which happens to be the same as 2 lots of the projection of L onto N. Okay, so from this diagram, L plus R is equal to 2 lots of the projection of L onto N. So rearrange very, very simply by subtracting R from both sides, and that gives you the reflection vector. Part C essentially gives you 3 vertices of a triangle and asks you to calculate the reflection vector for a light source that's located at the origin. So to calculate the normal vector for a triangle, okay, so calculate sequential vectors going in the anti-clockwise direction. So we've got this vertex minus this vertex as our first vector, and the third vertex minus the second vertex as our second vector. So cross product those together, we have the normal vector, but we need the unit normal, so we calculate the magnitude, and then therefore we divide by the magnitude to calculate the unit normal. Centre of the triangle, simply add these 3 vertices together and divide by 3. That gives us the centre. So the light source is light source is at the origin, so it's the origin minus the centre gives us the L vector, which is there. Okay, so if we project L onto N, okay, just to recall, that projection of L onto N is L dot N hat times N hat. Okay, so this is L dot N hat multiplied by N hat, which gives us this vector. And then I just plug those into this formula here. So 2 lots of the projection minus L gives me the reflection vector there.